Okay, let's start by looking at a few basic integrals and remembering how we did those back in an earlier unit. The easiest type of integral problem to work is one for which we have memorized an antiderivative formula for the integral. These are worked directly by memorizing the table that we've reviewed above. And here are a few examples. Notice that we give basic examples here for each of the three types of integration problems. So the first type of problem we have here is a family of antiderivative problems. We are given a function and we want to find all possible antiderivatives of that. Well, this one used the sum. Actually, we're using the constant multiple, sum, and power function rules all together, but basically we could do it all in our head very easily. So we have three terms. We're going to get three terms here plus the constant term. The power just goes up by 1 to 4, multiplied by the reciprocal of that new power. 1/4 times 3 is 3/4. Power goes up 1 here from 1 to 2, divide by 2. 2 divided by 2 is 1. Constant terms pick up an x as a factor, and then we have a constant term at the end. So pretty easy to do that in your head. We can plug into the rule, the thing that we have here. Actually, I've got a newer version, slightly edited version of this I'm going to show you. It looks like this now. So let's, so when you open the app, it looks something like this. Okay, and we can put in our formula right here. 3x cubed plus 2x plus 5. So 3x cubed plus 2x plus 5. Just like that, it graphs it. And we're not interested in the definite integral right now, so the best thing to do is just maybe let those be the same number so that kind of disappears. But then we want to see the antiderivative. And here's the family of antiderivatives plus C5. This is the C is 0 at the moment. And now that with the slider, I can slide this and change that value of C. And so we get this to shift vertically. Okay, so if that term wasn't there, we'd have the one with that C is 0 would be the one that's graphed right now. And so we can see that pretty easily there, okay? Okay, and there's the screenshot from what we just did. This is a similar one here. The family of antiderivatives of 4 over 3x squared plus 2 over x plus 5 square root of x. Again, we can rewrite this as power functions. 4/3 times x to the negative 2 plus 2x to the negative 1 plus 5x to the 1/2. Power goes down, let's see, power goes up 1 to negative 1 and multiplied by the reciprocal of that, just changes the sign to negative 4/3. Now this one, the power negative 1 or 1 over x is a different one. It's a little different than the normal power rule. This is the one that gives you the logarithm, remember? If we were trying to do the regular power rule, we'd end up dividing by 0, and we know that's a problem. What we actually get is the antiderivative of x to the negative 1. It's the natural logarithm of the absolute value of x. And in here we use our regular power rule. 1 plus 1/2 is 3/2, multiplied by the reciprocal. 2/3 times 5 is 10/3. Don't forget your plus c when the last integral sign disappears. There's the correct answer. But if we put it back in a similar form as we started, we would write this as negative 4 over 3x plus 2 natural log of x plus 10/3. X to the 3/2 is x to the 1 and 1/2, if in mixed number form. The x to the 1 is here, x. The x to the 1/2 is the square root of x. Because of this square root of x, both in the original and here, x has to be a positive number. So we can drop the absolute value because the absolute value of a positive number, x, is just x. And we can check that or see that on the calculator, on the GeoGebra, by typing in the original one right here. I use SQRT for square root and type that in. I just set these both to 0 again to get the no shading for definite integral. But when I checked antiderivative, we got this here. And actually on the newer version, it'll be like this. We can slide the C around and get different ones. The one to see this graph right now is the C of 0. Here's another one. F prime of x equals secant x times tangent x. F of pi over 7 is 5. What is f of x? So this is our second type of integral problem where we want to find a specific antiderivative. So f is a specific antiderivative of this f prime, and we have an initial condition that is 1 point on the function f. So we'll start by finding the family of antiderivatives. The antiderivative of secant x tangent x is secant x. Remember, the derivative of secant x is secant x times tangent x. So that's straight away pretty easy. Then we know that f of pi over 3, that's supposed to say, not 7, I don't know where that's a typo. F of pi over 3 is 5. What's f of x? Well, if we plug in pi over 3 for all the x's, we plug in a 5 for the y, right here, or for the f of x, we've got an equation we can solve. But let's see if we can simplify secant of pi over 3. Well, pi over 3, if we think of a circle of radius 2 centered at the origin, we can put this standard triangle of lengths size 1, square root of 2, 1, 2, and square root of 3, and the angles are pi over 2, 90 degrees. This angle here, which is our reference angle and our actual angle, rotational angle, is pi over 3, and the angle up at the top is pi over 6. So putting our angle in standard form, we see that we get this, it crosses this circle at the x being 1, y being square root of 3, r is 2, and theta is pi over 3. From that, we could read off any of the trig functions we want. For example, secant is reciprocal cosine, so it is actually r over x. So it's 2 over 1, or hypotenuse over adjacent. So it's 2 is for secant of pi over 3. Of course, you could have plugged in your calculator. It would have told you that as well. Subtract 2 from both sides. We get c is 3. Plug that back in place of the c here, and we have our specific antiderivative. And I've adjusted this down here so that I have that specific antiderivative graphed. So there you can see that specific one graph. Notice it's 1 over cosine of x, which is secant of x, another way to say that. And the constant is 3. And so you see that shifted up 3 from where it would normally be with it compared to being 0. How about this one? See if you can do this one yourself. The integral from 0 to 4 of 2 to the x dx. Well, first of all, it's a definite integral, so we need to make sure that it's continuous on that interval if we want to apply the fundamental theorem of calculus to find an exact value for the answer. In fact, 2 to the x is continuous everywhere, so that we can do that. The antiderivative of 2 to the x is 2 to the x times 1 over the natural logarithm of 2. And we want to evaluate that from 0 to 4. I can pull the 1 over log 2 out front of the parentheses here, and I just have 2 to the 4th minus 2 to the 0. 2 to the 0 is 1, 2 to the 4th is 16, 16 minus 1 is 15. So the answer is 15 over the natural log of 2, or approximately 21.64. Notice that if I do this in my little program, and I put in 2 to the x here, and go from 0 to 4, it shades the graph that we're trying to find. In this case, the area is all above the x-axis, so it is the area between the curve and the x-axis that is this green area. And it gives me an exact value right there of 15 over natural log of 2, which is what we got when we did it by hand. And then approximately here, which you could get by typing 15 over natural log of 2 in your calculator, or by typing this integral in your calculator. It will give you a decimal approximation. And of course, this GeoGebra app, the way I've got it set up, has given me both of those things. Okay, so those are just the most basic kind. So the most basic kind of integrals are the ones that we can find an antiderivative just by looking at it, because we're applying a real basic integral rule. The next step up would be integration by substitution. We'll review a couple of those in the next video.